differences in ampacities between ICEA 440 and National Electrical Code, or NEC, power cables and trays arise from several factors. Understanding these differences is crucial for ensuring safe and efficient electrical installations. Firstly, test conditions play a significant role. The NEC ampacity values are typically determined in accordance with the Institute of Electrical and Electronics Engineers, or IEA, 380 cable testing standard. In contrast, the ICEA P-54-440 ampacity values are derived from tests conducted in the 1970s, when the standard was initially created. These different test conditions can lead to variations in ampacity results. These variations may include cable spacing, ambient temperature, and tray construction, all of which can influence how heat dissipates from the cables. Secondly, assumptions and safety factors contribute to the discrepancies. The ICEA standard tends to be more conservative than the NEC in terms of the assumptions and safety factors used to determine ampacities. For example, the ICEA standard might assume a higher conductor temperature limit or a lower thermal resistance between the cable and the tray. These conservative assumptions result in lower ampacities when compared to the NEC values. This is because a higher assumed conductor temperature limit implies less capacity to handle additional heat, while a lower thermal resistance suggests a poorer ability to dissipate heat. Thirdly, depth of fill is another important factor. The ampacity of cables and trays significantly depends on the depth of fill, which represents the percentage of the tray area occupied by cables. A higher depth of fill means less air circulation around the cables, leading to increased heat buildup and consequently lower ampacities. The ICEA standard employs a NEMA depth of fill, which, in many cases, is more conservative than the actual fill depth. This conservative approach results in lower ampacities for the same cable in an ICEA calculation as compared to an NEC calculation. The NEMA depth of fill accounts for the physical space occupied by the cables, considering their diameter and arrangement within the tray. Finally, field experience also influences the perception of ampacity values. The NEC ampacity values have been extensively used in the field and have generally proven to be safe and reliable over time. On the other hand, the ICEA ampacity values, due to their conservative nature, may sometimes result in the underutilization of cables. This means that cables might be rated for a lower current carrying capacity than what they can actually handle safely under real-world conditions. In conclusion, the disparity in ampacities between ICEA 440 and NEC power cables and trays stems from a combination of factors. These include variations in test conditions, differences in assumptions and safety factors, considerations related to depth of fill, and the accumulation of field experience. While the ICEA standard offers a conservative approach, the NEC ampacities are widely regarded as more practical and reflective of actual operating conditions. It is essential to understand these differences to make informed decisions when selecting cables and designing cable tray systems. When determining the ampacity of a cable, it's crucial to consider several factors, including the cable's insulation type, size, installation method, and ambient temperature. The NEC provides tables, such as Table 310.16, that list the allowable ampacities for various conductors under specific conditions. These ampacities are based on the conductor's ability to dissipate heat without exceeding its insulation's temperature rating. However, these values must be adjusted for ambient temperatures higher than 30 degrees Celsius or 86 degrees Fahrenheit, as well as for the number of current-carrying conductors in a raceway or cable tray. For example, let's consider a number 2 American wire gauge, or AUG, copper conductor with THHN insulation, which has a temperature rating of 90 degrees Celsius. According to Table 310.16, this conductor has an ampacity of 130 amps when the ambient temperature is 30 degrees Celsius or less. If the ambient temperature is higher, a correction factor must be applied. These correction factors are also listed in Table 310.16 and vary depending on the insulation type and temperature rating of the conductor. Furthermore, if there are more than 3 current-carrying conductors in a raceway or cable tray, a derating factor must be applied to the ampacity. This is because multiple conductors generate more heat, reducing the overall heat dissipation capacity of the system. The directing factors are specified in NEC Table 310.15 cone and depend on the number of conductors. For instance, if there are 4 to 6 current-carrying conductors, the ampacity must be reduced to 80% of its original value. Cable trays are commonly used to support and route cables in industrial and commercial settings. The NEC provides specific guidelines for cable tray installations, including requirements for fill area, support spacing, and grounding. Section 392.9 ATWA specifies the maximum allowable fill area for multi-conductor cables and cable trays. For a 36-inch wide open ladder bottom tray, the maximum allowable fill area is 42 square inches. This limit ensures that there is sufficient space for air circulation around the cables, preventing overheating. The ampacity of cables and cable trays is also affected by the type of tray, the spacing between cables, and the presence of covers. Cables installed in ventilated trays with adequate spacing have a higher ampacity than those in solid bottom trays or trays with covers, as the ventilation allows for better heat dissipation. The NEC permits the use of ampacity adjustment factors for cables and cable trays under certain conditions. These adjustment factors are based on the number of cables in the tray and the tray's configuration. The goal is to ensure that the cables do not exceed their temperature ratings, even when installed in close proximity to each other. In addition to the NEC, other standards, such as those published by ICEA and NEMA, provide guidance on cable ampacity and installation practices. These standards may offer more specific recommendations for certain types of cables or applications. For example, ICEA P-54-440 provides ampacity ratings for cables based on depth of fill in cable trays. Understanding these standards and their differences is crucial for ensuring safe and reliable electrical installations. Let's consider an example to illustrate how these factors affect cable ampacity. Suppose we have a cable tray containing 41 number 2 AWG 90 degrees Celsius 0 to 600 volts class 3 conductor cables, each with an overall diameter of 1.13 inches. The cable tray is an open ladder bottom tray 36 inches wide, and the ambient temperature is 40 degrees Celsius. First, we need to determine the area occupied by each cable. The area of a circle is calculated as pi times the radius squared. In this case, the radius is half of the diameter, which is 0.565 inches. So, the area of each cable is approximately 1.3 square inches. With 41 cables in the tray, the total fill area is 41 times 1.3, which equals 41.123 square inches. This is less than the maximum allowable fill area of 42 square inches, so the installation complies with NEC requirements. Next, we need to determine the ampacity of the number 2 AWG cable. According to Table 310.16, the ampacity of a number 2 AWG copper conductor with THHN insulation is 130 amps at an ambient temperature of 30 degrees Celsius. However, the ambient temperature in this example is 40 degrees Celsius, so we need to apply a correction factor. The correction factor for THHN insulation at 40 degrees Celsius is 0.91. Therefore, the adjusted ampacity is 130 amps times 0.91, which equals 118.3 amps. Since there are more than 3 current-carrying conductors in the cable tray, we also need to apply a directing factor. Assuming all 41 cables are current-carrying conductors, the directing factor from Table 310.15 cone is 0.5. Therefore, the final ampacity is 118.3 amps times 0.5, which equals 59.15 amps. Now, let's compare this to the ampacity calculated using the ICEA P-54-440 standard. According to this standard, the ampacity of a number 2 AWG cable in a cable tray depends on the depth of fill. In this case, the depth of fill is calculated as the total cable diameter divided by the tray width. The total cable diameter is 41 times 1.13 inches, which equals 46.33 inches. Dividing this by the tray width of 36 inches gives a depth of fill of approximately 1.29 inches. Referring to Table 3.6 in ICEA P-54-440, the ampacity of a number 2 AWG cable at a depth of fill of 1.5 inches and an ambient temperature of 40 degrees Celsius is 85 amps. As you can see, the ampacity calculated using the NEC is significantly lower than the ampacity calculated using the ICEA standard. This difference is primarily due to the more conservative dating factors used in the NEC and the different assumptions about heat dissipation. In summary, determining the appropriate ampacity for cables and cable trays requires careful consideration of several factors, including cable size, insulation type, ambient temperature, fill area, and the applicable standards. It is essential to consult the NEC and other relevant standards to ensure that the installation complies with all safety requirements and provides adequate protection against overheating and fire hazard. Remember that these calculations are based on specific assumptions and conditions. It is always recommended to consult with a qualified electrical engineer or inspector to ensure that the installation meets all applicable codes and standards. Different types of cables have different insulation materials, each with its own temperature rating. Common insulation types include THHN, THWN, XHHW, and RHW. The temperature rating of the insulation determines the maximum allowable operating temperature of the conductor. Exceeding this temperature can damage the insulation and lead to electrical failures or fire hazards. Cable size is another critical factor in determining ampacity. Larger conductors have a lower resistance and can carry more current without overheating. The NEC specifies the allowable ampacities for various conductor sizes based on their insulation type and installation method. Installation methods also affect cable ampacity. Cables installed in free air have a higher ampacity than those installed in conduits or cable trays because they can dissipate heat more effectively. The NEC provides different ampacity tables for different installation methods. Ambient temperature plays a significant role in cable ampacity. Higher ambient temperatures reduce the cable's ability to dissipate heat, which lowers its ampacity. The NEC provides correction factors to adjust the ampacity for ambient temperatures above 30 degrees Celsius or 86 degrees Fahrenheit. The number of current-carrying conductors in a raceway or cable tray also affects ampacity. When multiple conductors are bundled together, they generate more heat, which reduces their overall ampacity. The NEC provides dating factors to adjust the ampacity for the number of current-carrying conductors. Cable trays come in various types, including ladder trays, solid bottom trays, and ventilated trays. The type of tray affects the cable's ability to dissipate heat. Ventilated trays provide better air circulation and allow for higher ampacities. The fill area of a cable tray is the percentage of the tray's cross-sectional area occupied by cables. The NEC specifies the maximum allowable fill area for cable trays to ensure adequate air circulation and prevent overheating. Grounding is an essential aspect of cable tray installations. Cable trays must be properly grounded to provide a safe path for fault currents and prevent electrical shocks. The NEC provides specific grounding requirements for cable trays. When installing cables in cable trays, it is important to follow the manufacturer's instructions and the applicable codes and standards. This will ensure a safe and reliable installation that meets all requirements. Regular inspections and maintenance of cable tray systems are also essential. This includes checking for damage, corrosion, and loose connections. Any issues should be addressed promptly to prevent electrical failures and ensure the continued safe operation of the system. In addition to the NEC, other organizations, such as the IEA and the ICEA, publish standards and guidelines related to cable ampacity and installation practices. These standards may provide more specific recommendations for certain types of cables or applications. It is important to consult these standards when designing and installing cable tray systems. Understanding the factors that affect cable ampacity is essential for ensuring the safe and reliable operation of electrical systems. By carefully considering these factors and following the applicable codes and standards, you can prevent overheating, electrical failures, and fire hazards. Always consult with a qualified electrical engineer or inspector to ensure that your installation meets all applicable requirements. The information provided here is for general guidance only and should not be considered a substitute for professional advice. When determining the ampacity of power cables and cable trays, it's crucial to understand the impact of conductor temperature rating. The conductor temperature rating refers to the maximum temperature that the cable's insulation can withstand without degradation. Common temperature ratings include 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. Higher temperature ratings allow for higher ampacities, as the cable can handle more heat without damaging the insulation. However, it's important to ensure that all components in the electrical system, including terminations and equipment, are rated for the same temperature as the cable. Mixing components with different temperature ratings can lead to overheating and potential failures. A national electrical code provides tables, such as Table 310.16, that list the allowable ampacities for various conductors based on their temperature rating and installation method. These ampacities are based on the assumption that the conductor will be operating at its maximum rated temperature under normal conditions. However, if the ambient temperature is higher than 30 degrees Celsius or 86 degrees Fahrenheit, a correction factor must be applied to the ampacity. These correction factors are also listed in Table 310.16 and vary depending on the insulation type and temperature rating of the conductor. In addition to the ambient temperature, the number of current-carrying conductors in a raceway or cable tray also affects the ampacity. When multiple conductors are bundled together, they generate more heat, which reduces their overall ampacity. The NEC provides directing factors to adjust the ampacity for the number of current-carrying conductors. These directing factors are specified in NEC Table 310.15 current and depend on the number of conductors. For example, if there are 4 to 6 current-carrying conductors, the ampacity must be reduced to 80% of its original value. The type of cable tray also affects the ampacity. Cables installed in ventilated trays with adequate spacing have a higher ampacity than those in solid bottom trays or trays with covers. This is because the ventilation allows for better heat dissipation. The fill area of a cable tray is another important factor. The NEC specifies the maximum allowable fill area for cable trays to ensure adequate air circulation and prevent overheating. Section 392.9 outward specifies the maximum allowable fill area for multi-conductor cables in cable trays. For a 36-inch wide open ladder bottom tray, the maximum allowable fill area is 42 square inches. When calculating the fill area, it's important to consider the overall diameter of the cable, including the insulation and any outer jackets. The ampacity of cables in cable trays is also affected by the spacing between cables. Cables installed with adequate spacing have a higher ampacity than those installed in close proximity to each other. This is because the spacing allows for better heat dissipation. The NEC does not provide specific spacing requirements for cables in cable trays, but it's generally recommended to maintain a minimum spacing of 1 cable diameter between cables. In addition to the NEC, other standards, such as those published by ICEA and NEC, provide guidance on cable ampacity and installation practices. These standards may offer more specific recommendations for certain types of cables or applications. For example, ICEA P-54-440 provides ampacity ratings for cables based on depth of fill in cable trays. The depth of fill is calculated as the total cable diameter divided by the tray width. The ICEA standard provides ampacity tables for various cable sizes, insulation types, and depths of fill. When using the ICEA standard, it's important to ensure that the cable tray is installed in accordance with the manufacturer's instructions and the applicable codes and standards. It's also important to consider the ambient temperature and the number of current-carrying conductors when determining the ampacity. Understanding the factors that affect cable ampacity is essential for ensuring the safe and reliable operation of electrical systems. By carefully considering these factors and following the applicable codes and standards, you can prevent overheating, electrical failures, and fire hazards. Always consult with a qualified electrical engineer or inspector to ensure that your installation meets all applicable requirements. The information provided here is for general guidance only and should not be considered a substitute for professional advice. When comparing ICEA 440 and NEC ampacity values, keep in mind that the ICEA standard is generally considered more conservative. This means that the ampacity values listed in the ICEA standard are typically lower than those listed in the NEC. The reason for this is that the ICEA standard uses more conservative assumptions about heat dissipation and ambient temperature. The ICEA standard also takes into account the effects of aging and degradation on cable insulation. As cable insulation ages, its ability to dissipate heat decreases, which reduces its ampacity. The ICEA standard includes deterring factors to account for this effect. The NEC, on the other hand, does not explicitly address the effects of aging and degradation on cable insulation. The NEC ampacity values are based on the assumption that the cable is new and in good condition. Therefore, it's important to consider the age and condition of the cable when determining its ampacity. If the cable is old or has been exposed to harsh environmental conditions, it may be necessary to derate the ampacity to account for the effects of aging and degradation. In addition to the effects of aging, it's also important to consider the effects of harmonics on cable ampacity. Harmonics are distorted waveforms that can increase the current flowing through a cable, which can lead to overheating. The NEC requires that cables be derated when they are supplying nonlinear loads that generate harmonics. The derating factors for harmonics are specified in NEC Table 310.15 Con. When designing electrical systems, it's important to consider all of these factors to ensure that the cables are properly sized and protected. Using the correct ampacity values is essential for preventing overheating, electrical failures, and fire hazards. Always consult with a qualified electrical engineer or inspector to ensure that your installation meets all applicable requirements. The information provided here is for general guidance only and should not be considered a substitute for professional advice. In summary, the ICEA 440 and NEC power cable ampacities in trays differ due to variations in test conditions, assumptions, safety factors, depth of fill considerations, and field experience. ICEA is conservative, while NEC reflects practical conditions.